All right. So today, our goal, we're going to be looking at um, three main scientists that contributed to gas laws. Overall, it's going to be four different equations that we get today. But so the first one, we'll be able to use Boyles Law to calculate volume pressure changes given a constant temperature. Second, we'll use Charles's law to calculate volume temperature changes at a constant pressure. And then we will also look at Guy Lussac, which he didn't mention in the video. Guy Lussac showed a relationship between pressure and temperature, given that the volume is the same. And then ultimately, we can take these three scientists and their contributions to understanding of gas and put them together in what's called a combined gas law to see a relationship between volume, temperature, and pressure at the same time. All of these are going to be before and after. So like you'll have a beginning set of pressures, temperatures, and volumes, and then you'll have an ending set of pressure, temperature, and volume, and its comparative relationships. So that's where we're starting today, and then we'll kind of go from there. All right. So to start off, we need to remember Dalton. So we've talked about Dalton a couple of times in this class, but Dalton also gave us something called kinetic molecular theory. Some of these statements will sound familiar, so I do want you to get these and copy these down because there are going to be some questions that relate to this. There are some things that we have a better understanding of it now than when Dalton wrote this. So if you remember, Dalton was kind of the person that also gave us atomic theory and those assumptions of atomic theory. These are very similar and related to those. So Dalton made the statement that gases consist of tiny molecules or atoms which are in continuous random motion. All right, we know that to be true today. Gases are made of atoms and molecules, and they are in continuous motion. Dalton also stated, the second statement was that the distance between the molecules is large compared to the size of the molecules themselves. That is true. Those molecules are very, very, very small. So in comparison to the actual area that they move around in. So the other way to state this statement is the volume occupied by gas consists of mostly empty space. So in between each molecule of the gas, there's empty space. There's a little, I guess it's an Instagram reel or a TikTok reel that shows the little guy getting arrested for assault or whatever, and he tells the police officer that, in class I learned that atoms never touch each other, and we're all made of atoms, so therefore I didn't hit that person, kind of thing. All right, that's in relative statement. That is true. These atoms move around. They do interact. They do collide. But technically, the atoms never touch because there's always some degree of empty space in between them. All right. Now, statement number 3. I'm going to put a little asterisk by statement number 3. So when Dalton was forming these postulates in, I forget the time, but I know it was 1800 something. When he was coming up with these, he had no way of really truly detecting this in experimentation. All right. So he made the statement that gas molecules have no attraction for one another. This is a statement that's true and false at the same time. We know that anything that has mass has the ability to have intermolecular forces. It has the ability to have some sort of gravitational attraction to each other. All right. So So what makes this false is we have now introduced the idea of intermolecular forces, last chapter, IMFs, um, basically saying that molecules do have some sort of attraction for each other. Even if they're non-polar, they're still going to have London dispersion, so they have these temporary dipoles. So when two atoms collide, two gas atoms collide, they're going to form a temporary dipole, and they're going to have London dispersion attraction. So that should slow the speed of the molecule down some. All right. That's the first one that we've made changes to. All right, number 4, it says gas molecules move in straight lines in all directions, colliding frequently with one another in the walls of a container. That's true. They do that. This is where we get the idea of pressure. These collisions cause pressure to exert on the walls of the container. That's why when you blow a balloon up, it gets larger. That's why when you put air in your tire, the tire gets more firm. That's why when you open up a soft drink, it has the little hiss noise, and sometimes you see the foam come out and things like that. All right. I'm going to come down to number 3. So, moving on. Number 5. This is another one that I'm going to circle and put an asterisk because this is one of those statements that, again, is true and false at the same time. When Dalton wrote the statement, he was using the best information he had. We have better information now that knows a little bit different. So the statement says that no energy is lost by the collision of a gas molecule with another gas molecule or with the walls of the containers. Dalton believed that all of the collisions were perfectly elastic, meaning no energy is lost. We know that to be false today, that there is some energy transfer from molecule to molecule. So it is not perfectly elastic, but in most situations, it is pretty close to being perfect. Close enough that we can just leave it alone. All right. We don't really have to identify it. But when we talk about collisions being elastic or not, we get into this idea of what's called an ideal gas versus a real gas. All right. We know that in the real world, there are things like friction and energy being transferred into heat and things like that, heat and light, due to collisions not being perfectly elastic. But in the ideal world, everything works out for us. We can actually treat gases as ideal when they have a low molar mass and it's happening in a high temperature environment, because the gases pretty much act like you don't notice the change in energy. The heavier the gas gets, the more we notice the change in energy. All right, and number 6, the last one, average kinetic energy for a molecule. Average kinetic energy for a molecule is the same for all gases at the same temperature. That is true. The energy, so if you have two different gases, if you have helium molecules, and if you have helium molecules and nitrogen molecules in the same container, they're at the same temperature, they have the same kinetic energy. The difference is the helium molecules will be moving much faster than the nitrogen because the nitrogen's a little bit heavier. All right, so remember that force is equal to mass times acceleration. So they're going to have essentially the same force. All right, it's just one's going to be moving faster than the other because of the mass. All right. So the average kinetic energy for molecules of the same gas for the same gases at the same temperature is directly proportional to the absolute temperature. So we can actually make a statement that temperature we can say temperature and kinetic energy are equal or directly related. As temperature increases, energy increases. As temperature decreases, energy decreases. So another way to state this, or a better way to state this maybe, would be increased temperature increases kinetic energy, decreased temperature decreases kinetic energy. All right. Now, so the four scientists that we're going to cover today are Boyle, Charles, Lussac, and Avogodro. Avogodro did a lot. We've already kind of talked about Avogodro and his relationship. It's going to come back to the mole of something, all right, and how the mole causes change. I treat Avogadro a little bit separate just because his relationship we can't use in combined gas law. So he's going to be a little bit on the outside, but we'll still look at him. All right. So there are some units, and if you take out your, no, I'm going to go through each one individually. All right. If you take out your periodic table reference packet, I do want to point out that a lot of this stuff you already have. I'm just going to go ahead and cover it once more just so that you can see it. All right, so down in that, on the second page of your packet, down in the bottom left-hand corner, what you'll definitely find information about this. All right, and I'm going to go through these things again. So when we're talking about gases, we do refer to STP. All right. Standard temperature and pressure. Remember that standard temperature is going to be 273 Kelvin or 0 degrees Celsius. We know those two to be the same number. And then standard pressure. The SI unit for pressure is kilopascal. In this class, I tend to like to use atmosphere because atmosphere is a cleaner number. If I can get it to write. And the way that we determine pressure on Earth is we have related it to what is the pressure of the atmosphere at sea level, and we designated that as 1 atmosphere. So if you go lower than sea level, air pressure gets greater. If you go higher than sea level, air pressure reduces. But because it's a number based off of 1, it's an easier number for us to do calculations with and things like that. All right, so there are some relationships, and we can relate all of these back to the atmosphere. Notice on your reference packet, it has this as well. So 1 atmosphere is equivalent to 101.33 or 325 kilopascals. 1 atmosphere is equal to 101,000 pascals. Remember, the difference between a kilopascal and a pascal is a factor of 1,000. 1 atmosphere equals 760 millimeters mercury, or 1 atmosphere equals 760 torr. I can tell you that 1 torr is a direct relationship to 1 millimeter mercury. These are actually the same unit of measure. Just torr is a given name to millimeters of mercury. In the United States, we refer to it as millimeters of mercury. Other places in the world refer to it as torr. Most of the time, in scientific situations, whether it be in a lab or in an engineering facility, you're going to see it related to as atmosphere in kilopascals. If you watch the news and watch the weather, you also know that sometimes they'll refer to air pressure in PSI. They'll refer to it in millibars, things like that. There's tons of different ways they measure pressure. I only want you to know atmosphere, kilopascal, millimeters mercury. That's the only ones I'm really concerned with. You might have a couple of questions that throw in torr, but we just have to be able to recognize those. All right. Other measurements that we're going to be using, volume. We're typically going to be measuring in liters, but realize we may have to convert from milliliters to liters, things like that. Temperature, always convert to Kelvin. For gas laws, always so degrees Celsius plus 273 equals Kelvin. All right. The reason why we always use Kelvin on these calculations is because if we use degrees Celsius, we can end up with negative numbers. And because we are multiplying and dividing, and then the temperature is going to use addition and subtraction at times, we can end up with some bad numbers on our calculation because negative numbers will throw the calculation off. All right. The first time I didn't, at one point I was trying to just prove, because I said, well, unit of Kelvin increase is the same thing as a unit of Celsius, but it really does give you bad numbers when you do these calculations. It's not going to give you a meaningful number. So there is a reason. All right. So our first scientist, Boyle. Boyle stated that if you hold temperature constant, remember, if something is constant, it means it all right. So since we're holding temperature constant, temperature does not change. So Boyle says at a constant temperature, the volume of a gas increases as the pressure decreases. So we have this relationship that volume will increase as pressure decreases. And so because we have that, we can look at a both before and after situation. We can look at a before and after situation, and we can get the formula that in the beginning circumstance, if we have an initial pressure that I'm going to call P1, an initial volume that I'm going to call V1, and then we change either the pressure or the volume. So P2 will equal V2. But if we increase the pressure, so if pressure 2 is greater than pressure 1, that means volume 2 has to be smaller. Or if we increase the volume, so if volume 2 is a greater volume than volume 1, pressure has to go down. All right. So this is what's called an inverse relationship. As one goes up, the other goes down. So if we were to graph volume versus pressure as far as the change in a situation, we're going to see it makes a downward moving curve. All right. I guess the best example that I can give you of this and that you would be familiar with is if you've ever taken the water bottles after you've drinking it and you squeeze, you twist it at the bottom and you pop the top off, you know that the pressure increases as you decrease the size of the bottle. Or if you squeeze a flexible container in some place, the pressure increases in another place. All right, that's how Boyles Law relates. So if you change the volume, the pressure changes, but as the volume goes up, the pressure goes down, or as the volume goes down, the pressure goes up. All right, so let's look at our packet. I'm going to show you a couple of these problems. I'm not going to answer it, solve it. I'm just going to walk you through a setup. So we're going to do an example for, so we're going to look at number one. That should be the first page in your packet. But if not, find the one that says Boyles Law, pressure and volume, and we will look at that. All right. So again, it gives us our formula right there, P1 times V1 equals P2 times V2. All right. So the question says, atmospheric pressure on the peak of Mount Everest can be low, which is why climbers need to bring oxygen tanks for the last part of the climb. If the climber can carry 10-liter tanks with an internal gas pressure of 3.04 times 10 to the fourth millimeters mercury, what will the volume of the gas be when it's released from the tanks at a pressure of 150 millimeters mercury? So what we need to be able to do to answer these type of questions is identify what things are what. So if I call this my P1, not P, what is liters? Sorry, volume. So if I call this my V1, then this has to be my P1. And then this is going to be my P2. And so we are looking for V2. So I can go ahead. I've already given you a place to put the givens. So my V1 was 10 liters. All right. My P1 is 3.04 times 10 to the fourth. If you want to write that in standard notation, you can. So it'd be 3,040 millimeters mercury. But I'm going to use it just like this. And then P2 is 150 millimeters mercury. Now, we want to know V2. So, let's see if I can get that to a better. All right. So now we have the equation P1 V1 equals P2 V2. I'm trying to solve for V2. So I'm going to manipulate this equation to get to V2. So the easiest way for me to do that would be to divide by P2 on both sides. That cancels there. And so that gives us P1 V1 over P2 equals V2. So I can rewrite my expression that V2 equals P1 V1 over P2. And then all you have to do is plug the numbers in and then solve. Your answer because you are dividing by millimeters mercury, your answer is going to be in liters. All right. I'll look at number 2 real quick just to kind of point it out. All right. So number 2, it says part of the reason that conventional explosions cause so much damage is that their detonation produces a strong shock wave that can knock things down. While using explosives, the shock wave can also be so strong that 12 liters of gas can reach a pressure of 3.8 times 10 to the 4th millimeters mercury. When the shock wave gas passes and returns to a pressure of 760 millimeters mercury, what will the volume of that gas be? All right, so again, we have 2 pressures, 1 volume. So that means we're going to be solving for V2 again. But if we were trying to solve for P2, again, we could manipulate the equation to get there. All right, so just be able to manipulate those equations. Again, I'm not so much concerned with you solving these right now. You can save those for later. So I'm going to go ahead and move on in the notes because I don't really want us working on these right now. I just wanted to show you setup and how to pick apart the problem. All right. So we are going to go ahead and look at Charles next. Charles set at a constant pressure. So instead of, unlike Boyle, where temperature remained constant, Charles held pressure constant. So he conducted his stuff where he had a flexible container where that the volume could increase and decrease, but the pressure would remain constant. So you can think of this one as kind of like a balloon, like the ones we blow up, or a hot air balloon, where pressure is going to remain constant, but the volume changes. So he said at a constant pressure, the volume of a gas increases as the temperature increases. So volume increases as temperature increases. So this one ends up being a direct relationship So another way to write this, that as volume increases, temperature increases. You can see this if you have the pressure sensors on your car tires and you're doing a long drive, you can see this happen in real time. You start off the morning, your pressures are going to be a little bit lower. As you drive your car more, the pressures are going to increase in your tires as they heat up. So as you heat up the tires, the pressure, not the pressure, well, we'll see it with pressure, we're seeing it with volume right here. All right. That's going to be, sorry, I got ahead of myself. That's Guy Lussac did pressure and temperature. All right. So the relationship, the equation that we get for this one is V1 over T1. So initial volume divided by initial temperature equals the new volume divided by the new temperature. So V2 over T2. What I will tell you about this one is these types of problems, when you are solving for temperature, whether it be T1 or T2, it's a little bit more complicated to get that number. All right, because if you're not careful, you end up with the inverse of the number. You end up with 1 over T1 or something like that. So some students, I'm not saying to write the equation like this, but some students find it easier to manipulate it if we do V1 times T2 equals V2 times T1. That is the same expression. It's just written where I manipulate it to where it doesn't have fractions in it. All right. And so this one is actually a little bit easier to manipulate when you're solving for temperature. But again, if you look at it, all I did was I multiplied T1 by both sides, I multiplied T2 by both sides, and I end up with that. All right. Now, moving back to the worksheet, at the bottom of that first page, we have Charles's law stated on there, and then there's an example problem. So let's go ahead and look at that. Again, I'm not going to actually solve it. I'm just going to help us set up the initial one. So let's go fit to width. I want to look at Charles's law. So remember, Charles is only looking at volume and temperature. He's holding pressure constant. The big thing that I want us to know about Charles's law, you can write it in your notes, is that remember that temperature must be in Kelvin. All right. So if the temperature is given in Celsius, we have to convert that before we do anything else. So looking at this problem, it says the temperature inside my refrigerator is about 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius and a volume of 5 liters, what will the volume of the balloon be when it is fully cooled by my refrigerator? So for this one, I have two temperatures. I need to decide which one I'm going to call my T1 and my T2. I'm actually going to call this 22 degrees Celsius my T1, and I'm going to call 4 degrees Celsius my T2. And then, it really doesn't. I'm doing that because this one's by itself. I like to solve for the n variable. All right. And then this one, I'm going to call V1. Now, it does matter that if you call this one T1, this one has to be V1. All right. Now, plugging it in. So my V1 is 0.5 liters. I do have to do some stuff to my temperatures. So I need to do 22 plus 273. That's going to give me 295 for my T1. For V2, that's what I'm solving for. So I'm not real sure why I can't draw a question mark. V2 is what we're solving for. T2 is 4 degrees Celsius. So 273 plus 4 gives us 277 Kelvin. All right. Now, manipulating the equation. V1 over T1 equals V2 over T2. That means I'm trying to solve for V2. So when I manipulate it, I'm going to go ahead and say that it is V1 times T2 divided by T1 equals V2. I always manipulate my equation before I enter my numbers. I find it easier to do that, and it helps me to get to the thing to solve rather than trying to manipulate it while I have numbers in there. All right, so we went temperature temperature from the beginning to the end went down. So that means, so temperature decreases, so volume should increase. Wait. Sorry. No. This one is direct relationship. Sorry. I was thinking Boyle. This one's a direct relationship. So in this one, because temperature is going down, volume should go down. So temperature is decreasing, volume should decrease. Sorry, that was my brain not working. Direct relationship, temperature decreases, volume decreases. And make sure you know that that is 295, not 2.95. All right. So now, again, I'm not going to solve it. I just kind of want you to see it and recognize how to do it. Your answer should end up being in liters because Kelvin's going to cancel Kelvin right here. All right. Again, just the overall setup. You have 0.5 liters times 277 K divided by 295 K. Kelvin. I do recommend putting that top part in parentheses, solving that first, and then dividing. Again, it shouldn't really matter, but sometimes the calculators will give you some weird numbers. All right. So again, there's a second problem. It says a man heats a balloon over in an oven. Initially, the balloon has a volume of 0.4 liters and a temperature of 20 degrees Celsius. Now, I'm not going to go ahead throughout everything, but we have a volume. We have a temperature, so I'm going to call that V1, T1, and we have a T2. So this time, again, we're solving for V2. So we would manipulate the equation again to get to V2. But we just have to be able to manipulate. Remember to change the temperatures to Kelvin before you do anything else. All right. Third scientist, Guy Lussac. Guy Lussac, basically, he dealt with pressure. So he said the pressure of a gas is directly proportional to its absolute temperature. So he made a relationship that as pressure increases, temperature will increase at the same rate. So if we look at it graphically, it's going to make a straight line going up at a constant rate. All right. So the equation for his is very similar to Charles's equation, except for we replace volume with temperature. So Guy Lussac is P1 over T1 equals P2 over T2. Once again, if you are trying to solve for a temperature as one of your unknowns, you might find it easier to start off with P1 times T2 equals P2 times T1. Notice that that is the same thing. I'm just putting it into where we're multiplying rather than having fractions, and that way you don't end up with 1 over t at the end and have to remember to take the reciprocal. So again, this one actually tells us in there it's directly proportional, so it is, once again, direct relationship.
Why did it have
I think that's just the graph I grabbed. This may have been the part that was known, and then that was just extrapolated. But like Charles's law, because there's a temperature, remember that temperature must be in Kelvin. The biggest areas where I see students make mistake with these calculations is they don't convert to Kelvin to solve the initial problem, and then sometimes the answer will be asking for the answer back into Celsius, and they don't convert back to Celsius. So that temperature conversion is very important. To use the formulas, we have to convert to Kelvin. After we are done with it, if we have a temperature, sometimes it may not be necessary to convert back to Celsius. All right, so looking at our packet, on the third page, there should be a equation for Lussac, where you have this one. It's actually on the second page, sorry. Second page, you have Lussac, where we have P1 over T1 equals P2 over T2. Again, reminder, convert to Kelvin. So if we're looking at this first question, it says you're ice fishing, something we have a lot of experience with here in Louisiana. The propane tank attached to your heater had a pressure of 562 kilopascals when you bought it. And the temperature was about 7 degrees Celsius. So we have a temperature, we have a pressure. We'll go ahead and identify those as our P1, 562.2 kPa. And then 7 degrees Celsius, so that would be, 273 plus 7, so it'd be 280 Kelvin. Check my math, because sometimes I miss something. It says, as the fuel in a tank gets used, the pressure of the tank drops to about 210 kilopascals. So our P2 is 210 kPa. And so we want to know T2 this time. Now, I'm going to manipulate this equation to get to T2 rather than the other way, just to kind of show you what you would have to do. So I'm trying to solve for T2. So I have P1 over T1 equals P2 over T2. The way I would approach this first is the first thing I'm going to do is multiply each side by T1. So that gets rid of T1 on this side, and I end up times T1 there. Now I still have to get rid of T2, so I'm going to end up multiplying T2 by both sides. Gets rid of it there, and then I end up with T2. And now I have to get rid of P1 on this side, so I'm going to divide by P1, get rid of that, and I put P1 down here. So I end up with T2 equals P2 times T1 divided by P1. Now, the reason why I wanted to show it like that is to show you why I use the other equation sometimes, where I have P1 times T2 equals P2 times T1. This one ends up being a lot easier to manipulate. When you do that. All right, it just saves a step. All right. Now, again, this is real basic algebra. This is stuff that a lot of you were probably, if you took algebra in 8th grade, you were doing it there. You should be able to manipulate variables in an equation to be able to solve. All right. And it works the same whether it's Charles's law or Lussac. You still have to manipulate for temperature the same way. All right. So just some little, what are these called? Anagrams or something like that. Ways that help you remember what's constant, which things are constant in each of the equations. So Boyles' law says temperature is constant. So you're looking at a relationship between pressure and volume. All right. Charles's law, pressure is constant. So we are looking at a relationship between volume and temperature. And then Lussac, volume is constant. So we are looking at a relationship between pressure and temperature. So for Boyles' law, because temperature is constant, I remember a BLT. For Charles's law, with pressure being constant, I remember cheese pizza. And Lussac, volume is constant, so I remember to eat my green veggies. All right. For me, I just tend to memorize the formulas. I don't do that, but some people like those kind of things. All right. Now, so if you noticed, all three of those equations, Boyles' law, Charles's law, and Lussac, what you might be able to notice is that we can really put all three of these equations together, and we can put it together in something called the combined gas law. So if I have the same number for temperature, that means temperature would cancel out. So that would give me Boyles' law, P1 times V1 equals P2 times V2. If pressure was held constant, so that means pressure would cancel itself out. That's V1 over T1 equals V2 over T2. If volume is held constant and volume cancels itself out, you get Lussac, P1 over T1 equals P2 over T2. So we can actually, instead of memorizing three separate equations, we can put them together in one formula, and we call this formula the combined gas law, that pressure times volume divided by the temperature equals the new pressure times the new volume divided by the new temperature. All right. Once again, if we're ever solving for temperature with one of these, you might find it easier. You might find it easier to write the equation P1 V1 times T2 equals P2 V2 times T1. All right. Where I just flip that to isolate the temperature a little easier. All right. As with any of them, I'm going to say this again. Temperature must be temperature must be in Kelvin. All right. And so we do have an example problem for combined gas law. So this is where I make the note. Remember that STP is 0 degrees Celsius in 1 atmosphere. So one of the things that a lot of these problems where we use combined gas law, it may just tell you that one set of conditions is happening at STP, and then it gives you the other set of conditions. So if it doesn't tell you 0 degrees Celsius in 1 atmosphere or 0 degrees Celsius in 101.3 kilopascals, we may have to remember that from time to time. So in this one, number 7, we have a 350 milliliter sample, so that's a volume of helium gas is collected at 22 degrees Celsius. Excuse me. That's a temperature, and 99.3 kilopascals, that's a pressure. It wants to know what volume, so that's going to be V2, would this gas occupy at STP, so T2, and P2. All right, so go ahead plugging everything in. We have 99.3 kPa. We have volume 1, 350 milliliters. Now, at this point, it is perfectly okay for me to leave my volume in milliliters. That just means that my answer is going to be in milliliters. All right, whenever we do this. So unless it asks for us to solve for a certain volume, we don't really need to change the units there. All right, and then T2, 22 plus 273, that would be 295 again. All right, and then we can do pressure 2 is 101.3 kPa. And then volume 2 is what we're solving for. And then T2 is 0 degrees Celsius, so it's 273 Kelvin. Now, kind of looking at these in relationship, we don't really know what's going to happen. We do know that as far as pressure and volume is concerned, pressure is increasing, so that means volume should decrease. But temperature is decreasing, so that means volume should also decrease. So in this particular one, we're looking for a decrease overall in volume. So we need to solve for V2. So P1, V1 over T1 equals P2, V2 over T2. So the first thing I will do is get rid of my T2. So that means T2 times P1 over V1 equals that. And then I'll get rid of my P2. So T2 times P1 times V1 divided by P2 times T1. And that'll give us our answer as V2. And then there's your situation. All right. Again, there should be another problem, and you just have to manipulate to see where you're at. Pay attention to if the pressures are not in the same unit. You may have to convert from one unit to another. All right. And then the last one I'm going to give you is Avogodro. Remember that Avogodro gave us a relationship of what a mole is, that Avogadro determined that 6.022 times 10 to the 23rd particles of something is equivalent to a mole. Another relationship that Avogadro gave us is that 1 mole of a substance, or 1 mole of a gas, occupies 22.4 liters. All of these experiments took place in the same realm. So what he actually discovered, what Avogadro actually discovered is that we can get these direct relationships that as the number of moles increases, so N stands for moles, volume also increases. Or as we add particles to a container, pressure will increase. So N equals mole. All right. So V1 over N1 equals V2 over N2, and P1 over N1 equals P2 over N2. So that's going to actually lead us to what we call the ideal gas law tomorrow, and we can work on those. Now, I do have some problems in your packet that relate to Avogadro's law, but actually, that one's going to be a little bit. Those will be a little bit different, so you can kind of work on those and things like that. I do want to kind of quickly. Let me stop the video.